I will start with some application. So let us look into DP formulation for a parking problem. So let us say a driver is searching for an affordable parking, and the parking area details are like there are n parking spaces, and the spaces are numbered from 0 to n-1, and after the last space n-1 there is a garage named n, so it's like the terminal state. And the driver begins at space 0, moves through the spaces in sequence, and so going from k to k plus 1. At each space k, the parking cost is ck. Okay, so if he wants to park at stage k, then the cost will be ck. A space is available for parking with probability pk. So this is the probability of whether the space is free or not. So parking space is free or not, right? And it is independent of the availability of other spaces. Okay, so this is independent of whether the other spaces are empty or not. So the driver can only determine if a space is free when he arrives at it. So driver cannot really see all the parking spaces. The driver will know only at the stage k, and driver will observe and then will know whether it is free or not. Upon finding a free space, driver decides whether to park or to move to the next space. Okay, so this is a parking problem, and we can write a dynamic optimization framework. So this is a sequential decision making problem. You start from some initial state 0, and then you go from k to k plus 1 and so on, and there is a cost to take certain actions at stage k, and obviously you have to kind of minimize the cost. If the driver somehow reaches the last parking space n-1 and doesn't park, then he is obliged to park at the garage. Okay, so this is like the terminal state, and the garage parking cost is c. So this is like the terminal cost gn, right? So the terminal cost is c. So determine a policy that minimizes the expected parking cost. Okay, so let us see the diagram for the parking problem. This is the case where the driver is there and starts from 0 and then sequentially goes to 1. So whether so if he decides to park at stage 0, the cost is c0, at 1 the cost is c1, and so on. Okay, at k it's ck, and so on. If in case he doesn't park until n-1, then he must park at the nth stage, which happens to be the terminal with the cost c. Okay, so the driver may park at space this 0 to n-1 at cost ck. This is the notation for the cost. If the space is free, then he will park with cost ck. If not, then continue to the space, to the next space k plus 1. Obviously continuing does not have cost, so the cost is only for the parking. So continues at k plus 1 at no cost. So assuming that the parking space is kind of not very big, right? So then you have to drive a lot. Let's say you have to drive like 2-3 kilometers to go to k plus 1. Then you have a cost that you have spent some petrol, right, to go to such a long distance. So that we are not assuming. So at space n, the driver must park at cost c. So what are the for the DP we need these things: states, control, and start state and terminal state. So the problem can be structured as a dynamic optimization problem with n stages. So this is a finite horizon problem, and artificial termination state symbolizing the park status. So obviously when you park, then you reach the terminal state. For every stage k equals to 1 to n-1, there are 3 distinct states. You can be in the terminal state or state f prime, which so we use this notation f prime to indicate that the state is free, and state f will indicate that the space k is occupied. So at the initial stage there are only 2 states, f prime and f. At the concluding stage, only the terminal state exists. The control decision at state f prime, the driver can either park or proceed to the next state. So basically we have split this problem in two cases, right? So it's the parking space is free or not free, right? So this is the case where the parking space is free. Then the driver still can decide, even if it's free, the driver can decide whether to park or not, or move to the next state. So no decision is available at states F and state T. So obviously no decision, because F means like it's occupied. So you don't have choice, right? If the state is occupied, then there is no decision to be made. You have to move on to the next state. Or if you end up into terminal state, then obviously also you don't have any decision to be made. You are in a terminal state. So from any location K, arriving at the termination state T incurs a cost Ck. So it's kind of, we are repeating this. So if a parking choice is made, obviously, so assuming that K is vacant. In the contrary case, the driver moves to the subsequent state without any cost. At the final stage, and the driver is compelled to park. So that's the final case we already mentioned before. So this is the DP form with the notations we have. So the cost, we use this J star K F prime. So F prime, if you remember, this is for the case when it is free, the parking space is free at the kth step. So what would be the cost in that case, right? So the optimal cost to go upon arrival at space K that is free. So obviously, as I said, if the parking space is free, a driver still decides whether to park or not. And J star F will be the optimal cost to go upon arrival at a space K that is taken. So this would be kind of a simpler case, right? So the parking space is already taken. And then you are thinking, what is your estimate of the cost, given that the current K parking space is taken? And of course, we have a terminal cost, the cost to go of the part or the terminal termination state. So for the cost to go when there is a parking space at the kth stage can be written like this. So this will be minimum of Ck, which is the current cost. So you are at the kth stage and you are at a state where parking space is there. So this is F prime, kth stage. Now if you do decide to park, then you know the cost you have to pay is Ck. If not, then you will look for estimated cost if you indeed decide to park in future, right, at K plus 1. So this is something you will, this is an estimate you are making for the cost, that is it good idea to park now, or you have some kind of an estimate for parking in future onwards. Okay, not necessarily K plus 1, but it could be it's a completely like tail cost, right? So now why did we write like this? The current parking cost is Ck, is clear, that's by definition. But what is this? So what is this estimated cost, right? So as you can see, this cost is more like a expected cost at K plus 1 onwards. So in K plus 1, if you go, you will be in either cases where the K plus 1 parking space is occupied or not occupied. Okay, at K plus 1. So you are at K, and at K plus 1, you will have either F or F prime. So either the parking space at K plus 1 is free or it's not free. Then you look for the estimated cost. So the probability of the parking space being free at K plus 1 is Pk according to our definition. So then the expected cost will be Pk for the free and the complement of that, which is 1 minus Pk for not free. So basically this is the expected cost. Okay, so this makes sense for the future cost is calculated like this. So this is for K less than n minus 1. Now if you are at the terminal state, which is we have discussed, this is like here, and you have n minus 1 and n. Now this case is special because here you are saying at n minus 1, if you decide to park at n minus 1, then the cost is obviously C n minus 1, and if not, then your cost is C. Okay, for parking in a garage, right? So here at k equals to n minus 1, it will be the minimum of this. So Cn minus 1 or C. Okay. So this is for the free case, and then for occupied case. Occupied case, there is nothing to do right now because you are supposed to move on. So you will do the estimated cost for the future only. Okay. So this is why you just look at the cost for the future, because there is no nothing to do now. So you will look at k plus 1 cost. So expected cost for k plus 1, this is similar to this. And if you are at k equals to n minus 1, and since this is the occupied case, at k equals to n minus 1, since you are in occupied case, obviously you have to move on, and you will go to the terminal state with a definite cost of C. Okay. And if you decide to park at some k step, then you reach some terminal state, and the way it is defined for the parking itself, there is no cost. So if you do decide to go to the terminal state, then J star kt will be 0. Okay. So this is the DP for the parking problem, and we can simplify this. So above DP algorithm can be written in a simpler and equivalent form. This can be done by introducing the scalars. So we can define this J hat k, and J hat k is the expected cost of cost at when it is free, and the cost when it is not free. And we can do this even before verifying whether the free or taken status is there. So in the previous case, it's like I arrive at the case step, and then I decide based on the two cases whether it is free or not free. But I could have written like this even before verifying whether it's free or taken status. So in this case, we can write for n minus 1 case. If I am at n minus 1, then it will be the cost will be minimum of Cn minus 1 or C, and then so then it is like, since I'm not deciding whether since I'm not verifying whether it's free or not, this is that case. So hence it could be either of these depending on whether it was free or not. Okay, so that's fine. So if I knew at n minus 1 that whether it's free or not free, I knew that I have to take, so if it is free, then I knew that I have to just compare Cn minus 1 and C. If it is not free, then I know that I have to go to the garage with C. So however, in this case, at k minus 1, I don't know without verifying, right? So I don't know if at k n minus 1 whether it's free or not. So then I'm looking at probability of being free at n minus 1 and probability of not free. So basically it's expected cost. So free and not free. Okay, and if it is free, then we will look at the minimum cost of Cn minus 1 and C. And if it is not free, I'm certainly going to the garage with C. And for the intermediate k, so this is a valid cost, which is expected cost at the kth step. I'm looking for the cost estimate of whether it's free or not. That case is taken here. If it is free, so it's like whether it is free or not free. If free, then minimum of the cost to park now and expected cost for k plus 1. If it is not free, then the cost for k plus 1 onwards. So this is a slightly different form of DP. So basically the whole point is to now park the car. Given these probabilities and all this, let's say, are given, then we can go ahead and try to solve this problem given that the cost is given to us. So we may try to go and solve this. So this is the DP model for the parking problem. Okay, so we saw an application of DP for the finite horizon case. Now DP, the way we understood so far is that we have states, we have control, but then we know that there can be extensions to this. In the sequential decision making problem, what we have assumed is that at kth step, we look for the control UK to go to the step k plus 1. But this, in some cases, there may be a dependency over some previous control as well. Okay, so we may want to generalize this a bit. So in that case, we may. So sometimes we may even ask what exactly is a state, right? Now in our naive in our naive approach, there is xk state, and we are supposed to take controls to go to xk plus 1. This is what we understand so far. But the definition of the state could be made in a way that anything that seems to be useful now to go to the next state can be a state for us. Okay, so one thing is when we don't necessarily look at the controls now, but there is a dependency for the controls from the past. So there is a lot of debate in this area about what exactly is a state. Okay, so this is 1963 by very famous Kalman, and what he proposed, one of his popular papers are Kalman filters. So in modern terminology, we say that the numbers which specify the instantaneous position and momentum of each particle represent the state of the system. So when you look at the dynamical systems, then you are looking at position, momentum. The state is to be regarded always as an abstract quantity. So this is something we should keep in mind when we solve dynamic program problem. State will be treated as an abstract quantity. Whatever is useful for me to make decisions in the next time will be a state for me. Okay. So intuitively speaking, the state is the minimal amount of information about the past history of the system which suffices to predict the effect of the past upon the future. So as you can see, this definition is now very general. Okay, is the minimal amount of information that you need currently to decide about the future. So this means that to solve a very generic set of problems, we need to be a bit generous with the definition of states. Now let us generalize this definition of states so that we can solve wide variety of problems, including Tetris. So we will try to model the Tetris game, which needs a little bit more generic view of state. So let us see this case where states depend on previous controls. Now if the states do depend on previous control, unlike saying u0 and then you are taking controls at the stage 1, or you are taking controls at stage 2, if in case controls also depend on the previous control, then you need to consider these pairs as well. Okay, so then you have to consider these as well. So the controls that you took in the past are now taken as states to decide on the next control u3. So you may say that this will be your x3, u0, u1, u2. This whole thing actually is your current state. Let us say tilde is defined to be like this, and this is used to predict now u3, which will be our next control. Okay, so that's what Kalman said, right? Any minimal amount of information that you need. So if there are problems where the current control depends on the control taken in the past, then we have to modify our states in this way. Okay, so this is one generalization. We will generalize this in many possible ways, but this is one possibility. We can call this time delay. Okay, so basically it depends on some previous time. Okay, now a bit of a diversion. So is large language model a dynamic optimization problem or a sequential decision making problem? So first of all, what is a large language model? The modern the modern large language models are pre-trained models, and the way these guys are trained is that you have sequence of tokens, it goes in, and you have, let us say, this whole sentence, and you mask some of these words which are supposed to be predicted. So this goes in, this goes in, this goes in, and the output should be this masked tokens, which are these guys. So this acts like a label. So essentially, large language models are nothing but next token prediction, and usually these are transformers. From the paper, attention is all you need. By Assis Vaswani et al. So this is the most cited paper in AI by now, and they proposed transformer around 2016. So correct me if I am wrong, 2016 I believe. And then so these are transformers are encoder decoder model, and then some LLMs are like encoder only, some are decoder only. So depends whether you are using BERT or you are using ChatGPT. So these models are trained on very large set of sequence of text. Now these tokens are not necessarily the words themselves. Sometimes they use something called subwords, so that may be very different from the actual words that you see. So this is pretty much LLM. There is this box transformer. It takes in sequences and it learns to predict next set of sequences. You mask some of these tokens that is supposed to predict, and that becomes the level, and that's how it's a supervised training, and you do it on very, very large text. Now for our purpose, we are into dynamic programming problem. So we ask whether next token prediction is a sequential decision making problem, right? And if it is, then what are the states, what are the controls, so and what could be the cost. And as we see this being a autoregressive type model, it does look like a sequential decision making problem, because it learns to take couple of words and it is supposed to decide. So this is like decision problem. It is supposed to decide what could be the next probable token. So sequential decision making problem sometimes you may see this as the set of actions that you will produce as a sequence may be seen as a way of next token prediction itself, depending on how you formulate it. So there was one work in this direction. It's called decision transformer. By Arvind, I forgot the first author. And so this is the guy, Perplexity, right? CEO of Perplexity, Arvind Srinivas. So he's one of the author, not the leading author, but it happens that I only remember one, like few of these names. So decision transformer paper is pretty much about that. That in RL or sequential decision making problems, I'm supposed to predict next set of actions, and that leads me to next set of states. So can we think of transformers as a tool for decision making as well?
All of these advances have so far occurred in perception. What we're interested in this talk is to think about how we can go from perception, looking at images, looking at text, and all these kinds of sensory signals, to then going into the field of actually taking actions and making our agents do interesting things in the world. And here, throughout the talk, we should be thinking about why this perspective is going to enable us to do scalable learning, like I showed on the previous slide, as well as bring stability into the whole procedure. So sequential decision making is a very broad area. And what I'm specifically going to be focusing on today is the one route to sequential decision making, that's reinforcement learning. So just as a brief background, what is reinforcement learning? So we are given an agent who's in a current state, and the agent is going to interact with the environment by taking actions. And by taking these actions, the environment is going to return to it a reward for how good that action was, as well as the next state into which the agent will transition, and this whole feedback loop will continue. The goal here for an intelligent agent is to then, using trial and error, so try out different actions, see what rewards will lead to, learn a policy which maps your states to actions such that the policy maximizes the agent's cumulative rewards over time horizon. So you take a sequence of actions, and then based on the reward you accumulate for that sequence of actions, will judge how good your policy is. This talk is also going to be specifically focused on a form of reinforcement learning that goes by the name of offline reinforcement learning. So the idea here is that what changes from the previous picture where I was talking about online reinforcement learning, is that here, now, instead of actively interacting with the environment, you have a collection of log data of interactions. So think about some robot that's going out in the fields, and it collects a bunch of sensory data, and you've all logged it. And using that log data, you now train another agent. It could be another robot to then learn something interesting about that environment just by looking at the log data. Okay, so there's no trial and error component, which is currently one of the extensions of this framework, which will be very exciting. So I'll talk about this towards the end of the talk, why it's exciting to think about how we can extend this framework to include an exploration component and have trial and error. Okay, so now to go more concretely into what the motivating challenge of this talk was, now that we have introduced RL. So let's look at some statistics. So large language models have billions of parameters, and today they have roughly about 100 layers in transformer. They're very stable to train using supervised learning style losses, which are the building blocks of autoregressive generation, for instance, or for mass language modeling, as in BERT. And this is like a field that's growing every day. And there's a course on it at Stanford that we're all taking just because it has had such a monumental impact on AI. RL policies, on the other hand, and I'm talking about deep RL, the maximum they would extend to is maybe millions of parameters or 20 layers. And what's really unnerving is that they're very unstable to train. So the current algorithms for reinforcement learning, they build on mostly dynamic programming, which involves solving an inner loop optimization problem that's very unstable. And it's very common to see practitioners in RL looking at reward curves that look like this. So what I really want you to see here is the variance in the returns that we tend to get in RL. It's really huge, even after doing multiple rounds of experimentation. And that is really at the core got to done with the fact that our algorithms, learning objectives, need better improvements so that the performance can be stably achieved by agents in complex environments. So what this work is hoping to do is it's going to introduce transformers. And I'll first show in one slide what exactly that model looks like, and then we're going to go into deeper details of each of the components.
I have a question. Yeah, can I ask a question real quick?
Yes. And
thank you. What I'm curious to know is what is the cause for why RL typically has several orders of magnitude fewer parameters?
That's a great question. So typically, when you think about reinforcement learning algorithms, in deep RL in particular, so the most common algorithms, for example, have different networks playing different roles in the task. So you'll have a network, for instance, playing the role of an actor, so it's trying to figure out a policy, and then there'll be a different network that's playing the role of a critic. And these networks are trained on data that's adaptively gathered. So unlike perception, where you will have a huge data set of interactions on which you can train your models. In this case, the architectures and even the environments to some extent are very simplistic because of the fact that we are trying to train very small components, the functions that we're training, and then bringing them all together. And these functions are often trained in not super complex environments. So it's a mix of different issues. I wouldn't say it's purely just got to do with the fact that the learning objective is at fault, but it's a combination of the environments we use, the combination of the targets that each of the neural networks are predicting, which leads to networks which are much bigger than what we currently see, tending to overfit. And that's why it's very common to see neural networks with much fewer layers being used in RL as opposed to perception.
Thank you.
You want to ask a question?
Yeah, I was going to. Is there a reason why you chose offline RL versus online RL?
That's another great question. So the question is why offline RL opposed to online RL? And the plain reason is because this is the first work trying to look at reinforcement learning. So offline RL avoids this problem of exploration. You are given a log data set of interactions. You're not allowed to further interact with the environment. So just from this data set, you're trying to unearth a policy of what the optimal agent would look like. So it would...
Right, but like if you do online RL, wouldn't that like just give you this opportunity of exploration, basically?
It would. What it would also do, which is technically challenging here, is that the exploration would be harder to encode. So offline RL is the first step. There's no reason why we should not study why online RL cannot be done. It's just that it provides a more contained setup where ideas from transformers will directly extend. Okay, sounds good. So let's look at the model. And it's really simple on purpose. So what we're going to do is we're going to look at our offline data, which is essentially in the form of trajectories. So offline data would look like a sequence of states, actions, returns over multiple time steps. It's a sequence. So it's natural to think of us as directly feeding as input to a transformer. In this case, we use a causal transformer as it's common in GPT. So we go from left to right. And because this data set comes with the notion of time step, causality here is much more well intended than the general meaning that's used for perception. This is really causality, how it should be in perspective of time. What we predict out of this transformer are the actions conditioned on everything that comes before that token in the sequence. So if you want to predict the action at this t-1 step, we'll use everything that came at time step t-2, as well as the returns and states at time step t-1. Okay. We will go into the details of how exactly each of these are encoded. But essentially, this is in a one-liner. It's taking the trajectory data from your offline data, treating it as a sequence of tokens, passing it through a causal transformer, and getting a sequence of actions as the output. Okay, so how exactly do we do the forward pass through the network? So one important aspect of this work, which is we use states, actions, and this quantity called returns to go. So these are not direct rewards. These are returns to go, and let's see what they really mean. So this is our trajectory that goes as input to this number. And the returns to go are the sum of rewards starting from the current time step until the end of the episode. So really what we want the transformer is to get better at using a target return. This is how you should think of returns to go as the input in deciding what action to take. This perspective is going to have multiple advantages. It will allow us to actually do much more than offline RL and generalizing to different tasks by just changing the returns to go. And here it's very important. So at time step 1, we will just have the overall sum of rewards for the entire trajectory. At time step 2, we subtract the reward we get by taking the first action and then have the sum of rewards for the remainder of the trajectory. Okay, so that's how we call it returns to go. Like how many more rewards in accumulation you need to acquire to fulfill your return goal that you set in the beginning. What is the output? The output is a sequence of predicted actions. As I showed in the previous slide, we use a causal transformer, so we'll predict in sequence the desired actions. The attention, which is going to be computed inside the transformer, will take in an important hyperparameter k, which is the context length. We see that in perception as well here. And for the rest of the talk, I'm going to use the notation k to denote how many tokens in the past would we be attending over to predict the action at the current time step. Okay, so again, digging a little bit deeper into code, there are some subtle differences with how a decision transformer operates as opposed to a normal transformer. The first is that here, the time step notion is going to be have a much bigger semantics that extends across 3 tokens. So in perception, you just think about the time step per word, for instance, like in NLP or per patch for vision. And in this case, we will have a time step encapsulating 3 tokens, one for the states, one for the actions, and one for the rewards. And then we'll embed each of these tokens and then add the position embedding as is common in a transformer. And we feed those inputs to the transformer. At the output, we only care about one of these 3 tokens in this default setup. I will show experiments where even the other tokens might be of interest as target predictions. But for now, let's keep it simple. We want to learn a policy. A policy is just trying to predict actions. So when we try to decode, we'll only be looking at the actions from the hidden representation in the prefinal layer.
Okay. So I won't go into the detail of this paper now, but you can pick up as a project for this. It will be listed as a project very soon. You can explore this. So I will just describe the model and then move on to something else. So large language models, specifically the next token prediction type, could be seen as current text window, which is our state xk, And then the choice of the words that we will take is decided by the control UK. And once I do take the choice of the control, I end up taking that text and incorporating that text as a next text. And then I move on and I keep repeating this, and then I keep producing next set of sequence and so on. And some of these ideas could be mixed with other things which is happening recently, like for reasoning purpose as well. So something called chain of thought reasoning and so on. So how will, given a problem to LLM, can it produce a chain of thoughts, so one thought after the other? Because when we solve a problem, let's say maths problem, then we do have a sequence of steps that we take to solve the problem. So can these LLMs also work in a way that they can kind of take decisions and they can be guided via some cost or reward depending on they solve the problem or not. So in a higher level, we can even think of some chain of thought being applied. So thought 1, thought 2, thought 3, and how to go from T1 to T2 is the decision that it's supposed to take. And the way it will be decided by the overall the reward and so on. It could be some intermediate rewards and so on. So there will be the cost, just like in the sequential decision making framework. So some of these recent papers are actually doing this. The reasoning is enhanced by reinforcement learning now.
Imagine this, one single day and poof, Nvidia loses almost $600 billion in market value. What happened here? The answer lies in one word: DeepSeek.
The last couple of days I've been reading about China and some of the companies in China, one in particular, coming up with a faster method of AI and much less expensive method, and that's good.
Today, we dive into a groundbreaking research paper by DeepSeek titled DeepSeek R1: Incentivizing Reasoning Capability in LLMs via Reinforcement Learning. This paper introduces a state-of-the-art open-source reasoning model and provides a detailed recipe for training such models using large-scale reinforcement learning. The method is called Group Relative Policy Optimization, or GRPO in short. It was developed in-house at DeepSeek. Given a model we want to train and an input problem, we feed the input into the model and sample a group of outputs. Each output consists of a reasoning process and an answer. The GRPO method then observes these sampled outputs and trains the model to yield the preferred options. It is doing so by calculating a reward for each output using rules. One set of rules is used to calculate an accuracy reward. For example, in the case of math problems with deterministic results, we can reliably check whether the final answer provided by the model is correct. For code problems that come with predefined test cases, a compiler is used to generate feedback based on the test cases. Another type of rules helps to create format rewards. In the following table from the paper, we can see how the model is instructed to provide an answer, putting its thinking process within think tags and the answer within answer tags. The format reward enforces the model to follow this formatting.
And recently you have seen models like DeepSeek. They rely heavily on RL for reasoning. Okay, so they are now as good as OpenAI O1 model, and in some benchmarks they can beat OpenAI. And apparently they can train in very cheap way. They introduce some compute efficiency, some algorithmic enhancement, and they can train much faster. So these ideas are combined. Next word predictions, RL, there is a lot of work going on right now in this direction, how to mix and match power of LLM with decision making, especially if it has to do long chain of thought. Okay, now coming back to increasing our or generalizing our definition of states. So one possibility is we introduce so-called time delays. So by time delay, it means nothing but what I said before. It depends on the previous states and control. Okay, so let us see a simpler case where my current state depends on just the previous state. So the xk depends on xk minus 1 and the previous control uk minus 1. So we can again write it. So my current state xk plus 1 will depend on xk, the previous state xk minus 1, uk minus 1. And then the starting one is given like this. So it is about readjusting your state variables now. So you introduce some new state variables like yk, and you call it yk is xk minus 1, and you introduce another variable zk so that you don't confuse with the use, and zk is your uk minus 1. Then your new state variable at k plus 1 is like this. So xk plus 1 is like this, because yk is xk minus 1 and zk is uk minus 1, and with this matches with this, right? So with this variable, introducing new variables, we could write like this. Now it is kind of a trick, you can say, that we just want to see k plus 1 here and we want to see k here, but inside this k we know that it is actually dependent on k minus 1, and zk is actually depending on k minus 1. But for a compressed notation, we introduce these variables so that we have this view k plus 1 depends on k. So we can redefine our state to be like this. So xk tilde is our new state, which is xk, and yk, which was xk minus 1, and zk, which was uk minus 1. And in this new notation we can write it again like this, a familiar notation where xk plus 1 is fk xk, uk is the control, current control, and wk are the disturbances. So this is how we can incorporate, let's say, one time delay. So in this case it depends on k minus 1 as well, but obviously from here you can see if it depends on two previous controls, you can incorporate it here. It's just that you have to introduce more variables, and this state vector will increase in size, but this is how we can generalize the state. Okay, so using previous equation, we can now define the cost also in terms of x tilde k, and this leads to a problem divide of time delays, at least in notation terms. So now we see this as k and k plus 1 problem. The control uk is now influenced by the new state xk. Consequently, a policy should be comprised of functions from uk that consider the current state xk. It should also account from the previous state xk minus 1 and uk minus. So this is just the same thing said in terms of policy mu k. We know that policy xk tilde is nothing but uk. So if we apply the DP algorithm to the revised problem, then we can write down these with time delay. So at the terminal state, obviously we have gn xn, and at n minus 1 stage we know that the cost depends on n minus 1, but it depends on the previous state and the previous control as well. So that's why you see these. So everywhere you see these previous ones. So in general the DP is like this, and if you want to see this as the kth step, so here we are not using the x tilde thing here. Here we explicitly are kind of writing it in expanded form. So if you prefer in compact form, you can always write like this as well. So our cost at the kth step, it depends on the previous state, previous control, and everywhere your cost will depend on the previous state and control. So, and the cost to go for the initial state will be given by this. So there are potential alternative formulations when there are time delays either in the cost or the control constraints. So for instance, when the cost is this, so yeah, so here it's like it depends only on the previous state xk and on the current control. So these are some variations depending on what are the dependencies for the problem. So in extreme cases, it may happen that it depends on all previous states and all previous controls and all previous disturbance. This will be a very bad problem to solve, obviously, because if I have to really remember all the previous states, like as if I'm trying to predict stock prices of Apple tomorrow, and as if like I need to remember everything since the beginning when the Apple IPO was listed, which is not necessarily a good idea. So, but this is from modeling perspective, yes. In the extreme case, one may think of very extreme cases. It depends on all previous states, all previous controls, all previous disturbance, and so on, right? But okay. So then again, in those cases, you may generalize to and write this as xk tilde and take all those as combined state and so on. So anyway, these are a bit too much. Now let us. So we saw. So what we saw so far is time delay, where we said that our current state may depend on previous state and previous control. Now there is something called forecast. Now DP with forecast, and this will be useful in the Tetris as well. So let us see what is forecast. So at time k, controller can access a forecast yk. The controller has some information about the forecast yk. So this means that one has to reassess the probability distribution of the upcoming disturbance wk and the possible future disturbances. Okay, so somehow at state k you got some forecast. Now that forecast has consequence on the control that you are going to take now and the possible disturbance that can come. So we are kind of generalizing this. So the forecast yk could either be an exact prediction of wk. So let's say the disturbance that we are going to expect could be an exactly, it will tell us the disturbance, or a determination that the probability distribution of wk belongs to a specific set from a finite collection of distributions. Now remember, in our model, what we have is xk plus 1 is some f xk, uk and wk. Wk are the disturbances, so basically they are random variables, but the problem is that we don't know wk belongs to which probability distribution, right? So it may come from normal distributions, it can come from Bernoulli, binomial, geometric, and it may come from distributions that are not even the classical ones that we know, right? So those are the popular distributions that we know, but it may happen that wk may not follow any of the existing ones that we know. So if there is a forecast, somehow that tells me, look, this is what is going to happen with the disturbance wk, then it becomes deterministic and the problem is solved. If not, then that forecast can tell me what could be the nature of wk. By nature here we mean maybe it gives me an idea that this is going to be some normal distribution. The disturbance will be there, but it will follow normal distribution, or the distribution or it might follow Bernoulli distribution or Poisson distribution or so on. So this forecast depends now whether it will make it precise or it will narrow down the distribution. So the practical forecast of interest include, for example, probabilistic predictions regarding the state of the weather. So this itself has consequence in sequential decision making. So for example, we want to do something, let's say want to go and play some sports outside, then obviously this forecast, which we will rely on some agency that will give us the forecast, and this will have consequence on the action that we will take. Now if this forecast is such that the probability of rain in the forenoon is 90% and probability of rain in the afternoon is 10%, then certainly it has a consequence on my control that whether I should go and play in the forenoon or whether I should go and play in the afternoon. So forecast is helping you decide your control or the actions that you're going to take. Now it could be predictions about the interest rate for the money, or it could be the one done by RBI, and that has consequences on the stocks, inflation, and so many things. So that can impact your decision making. Predictions about the demand for inventory. So are there any predictions? Okay, so let's say some festival is coming nearby, and during those festivals there is a spike in the inventory, and on which days, let's say if this festival is around like for several days, then what could be the distribution of the disturbance W or the spike in this case in the demand, what curve it might follow, right? So maybe on some day it will spike very high, and then other times it will be moderate. Okay, so to manage forecast in control processes, what will you do? Because now it is about state. So far what we understand is state xk and xk plus 1 and uk, but now uk depends on forecast yk. So we got to kind of incorporate this in the model, in the DP model, how to use this. So introduce additional state variables corresponding to the information forecast provides, and illustration we will see this, I hope. So assuming that at the beginning of each state k, the controller receives an accurate prediction of the next disturbance wk, then it will be selected according to a particular probability distribution out of a given collection of these distributions p1 to pm. So that could be one possibility. If forecast is I, let's say, meaning it will follow pi distribution, then wk must be selected according to pi. So let's say if it's normal, pi is normal distribution, then wk will be sample from normal distributions, and then we will compute the average cost. Right, we will do a couple of sampling, Monte Carlo sampling that we saw, and then we will do the expected cost for w following that distribution, right? Okay, so let us formulate this. So the forecasting equation is represented as yk plus 1 is ik, and yk plus 1, let's say, can assume values in the set 1 to m, representing m possible forecast. A random variable jk assumes I with probability pi, and when jk takes the value I, the disturbance wk plus 1 will follow the distribution pi. So that's what we said. So then, combining the system and the forecast equation, we get this augmented system. So xk plus 1 is fk xk uk, and our forecast is given by jk. So obviously forecast will also decide the control that I'm going to take. So we can combine this x tilde as xk yk, and we can also combine wk tilde as wk jk. So the probability distribution of w tilde k is governed by the distribution pi, because the random variable jk is from the distribution pi, and it depends explicitly on x tilde via yk, but not on any prior distribution disturbance. So it does not depend on previous w. Okay, so reformulating the cost, control can be represented as stochastic dp. The control depends on both current state and current forecast, and for the forecast we can write this dp algo. So for the nth step, the terminal state, we reach the terminal state, so there is no we end the thing, so we don't have anything to do there. So it will be the terminal cost. You already reached there, so there is no decision to be made, no forecast, nothing to be used. And at the kth step, you are at a current state xk, and you are given some forecast information yk. Then you are supposed to compute the cost. So that cost will be gxk uk wk, the current cost, and the future cost, the expected future cost. Now this is written as expected cost, because you can see this is pi, right? So pi is the probability of following following one distribution, right? So that's why we wrote this as expected, and this is the cost from k plus 1 onwards. So given the observation yk, what would be the expected cost from k plus 1 onwards? Okay, so this is what it means, given the observation yk at the current k, because given the observation thing yk, then w will follow one of the distributions. and we will take the expected cost according to that distribution here. Okay. So here we have assumed that yk assumes the values in the set 1 to m. So yk assumes values in the set 1 to m. So this is a discrete PDF. So if it's there are m possible observations, then what is the likelihood of 1, likelihood 2? So if you have like 6-sided die, then the possibilities you have are 1, 2, 3, 4, 5, 6. So you can think of m as 6. And then with forecast, so it will follow certain distribution of the die. Now die may be uniform, die may be biased, whatever, right? It is a discrete distribution. But if we follow uniform distribution, then the probability of then this pi will be 1 over 6, right? But as I said, it may be a biased one. Die is a so if we take a regular die, then it has each of the 1 to up to 6 has are equally likely, whereas it may not be the case here. Okay, but it depends on the distribution at hand.
Ludo is a strategy board game for 2 to 4 players, in which the players race their 4 tokens from start to finish, according to the rolls of a single die. Ludo consists of a square board with 4 different colored bases in each corner. The first colored square outside of each base is the starting position. A path leads clockwise around the board, returning to a path the same color as the base, the home color, leading to the center home triangle. What do you need to play the Ludo game? A Ludo game board, 4 sets of colored tokens, green, yellow, red, and blue, and 1 6-sided die. Let's start the game. 2 to 4 players begin by placing their 4 tokens in their starting bases. Each player chooses one of the 4 colors. Now place all 4 tokens of that color in the starting base. Each player takes turns throwing the die. The player with the highest roll plays first. The players to the left follow in turn going clockwise. On each player's turn, the player rolls the die to determine how many squares they will move. The number on the rolled die will determine the number of squares the chosen token moves forward. The goal of the game is to move all 4 of the player's tokens clockwise once around the board, up the home column, and into the home triangle. To begin, a player must roll a 6 to move a token out of the base and onto the starting square. That token is then in play. If the player does not roll a 6, the turn passes to the next player. The player cannot make any moves until at least one token is in play. Once a player has one or more tokens in play, he selects a token and moves it forward along the track the number of squares indicated by the die. Players must always move a token according to the value rolled. Passes are not allowed. If no move is possible, the turn moves to the next player. Rules of the 6s. When a 6 is rolled, the player may choose to advance a token already in play, or may enter another staged token to its starting square. Rolling a 6 earns the player an additional or bonus roll in that turn. If the bonus roll results in a 6 again, the player earns an additional bonus roll. If a 6 is rolled 3 times in a row, that player loses his turn. The turn immediately passes to the next player. Landing on a shared square. If a player's token lands on an opponent's token, the opponent's token will set back to their base, where he must roll a 6 again in order to move out onto the starting square. If the player does not roll a 6, the turn passes to the next player. If a player captures the piece of another player, they are awarded a bonus roll. If in the bonus roll another player's piece is captured, another bonus roll is awarded, and so on. If a player lands on a square occupied by one of his own token, that space becomes blocked. A blocked square cannot be passed. Doubled pieces may move half the number if an even number is thrown. For example, move 2 spaces if a 4 is thrown. A doubled piece may capture another doubled piece. A doubled block also blocks trailing pieces of the player who created the block, or blocks them unless they roll the exact number to land on the block. Additionally, the doubled block cannot move forwards until the block that landed upon it moves off again. This reduces the tactical advantage of a block and makes the game more interesting. Safe squares. There are 4 safety squares on the board. These 4 safe squares are in each quadrant. Normally, the 4th square from the top in the rightmost column. All 4 starting square are also a safe square for all players. These squares are usually marked with a star. If any of your token is on a safe square, opponent's tokens can't send your token back to your base if their token lands on your token. How to win the game. A player cannot move their first piece into the home column unless they have captured at least one piece of any of the opponents. When a player's piece has reached the home column of its own color, the piece continues its moves towards the center to its home triangle. When a player's die roll lands its piece on the home base, that piece has completed its journey. A piece can only be moved to its home base with the exact roll. For example, if you roll a 5 and your token requires to move only 3 squares, you have to move another token or pass. The first player to move all his tokens to the finishing square wins the game. The remaining players continue to play to determine 2nd, 3rd, and 4th place finishers.
So given the yk observation, it follows certain probability distribution with possible outcomes 1 to m. Now what are the probabilities of having those outcomes? It depends on the distribution itself. Okay, so expectation over W is with respect to the distribution of the yk, right? So whatever distribution yk is, and we will take expectation based on that. So first thing is yk can come from one of these m. So these m themselves are some probability distributions, right? P1, P2, Pm. So yk may follow one of these. Okay, so it's like, what is the so there will be an expectation of yk over these. Like, what is the probability that it will be likely a distribution corresponding to the kth distribution, right, or the ith distribution, like that. So this is for that. So this is for that. What is the yk following which distribution? So what is the expected value for that? And then once the yk is observed, then wk belongs to the distribution of pyk. So one of these will be pyk. Okay, so one of these p will be pyk, and once that distribution is known, let us say whatever distribution is there, uniform or whatever is there, over that distribution you see this expectation here. I hope you are following me. There are two expectations happening here, right? This is also an expectation, and this is also an expectation. This inner expectation is like y can be one of the many distributions, right? So the expected value for that, and once y is known, then y gets fixed, and then we are supposed to look for what are the expected cost with wk. Okay, I hope it's clear. We are trying to make our DP problem more generic. In fact, this is what we need to solve Tetris game. Okay, because we will have observations forecast for some next set of piece that might be coming in the next step. Okay, so so this formulation can be extended in several ways. Forecast can be influenced by control action, like playing more for better forecast. So you may play a lot more so that you have better forecast. Implementing these extensions may make the DP algorithm more complex. So that's understandable because we have this hierarchy now. Okay, so we will come back to this model of forecast. So problems with uncontrollable state components. So let us see what this type of problems are. So in many problems of interest, the following observation can be made. The natural state of the problem consists of several components, okay, some of which cannot be affected by the choice of the control, and in those cases DP can be simplified considerably and be executed over controllable components of the state. Okay, so there will be so there will be some components of the problem that it's not in our hand. So basically, no matter which choice of control I take, those components cannot be controlled. So anyway, like I cannot do much about those because the only thing I can do is choose a set of controls. And if there is something uncontrollable, then we cannot really. So we can only look at the controllable components of the state. So consider a system with state components xk and yk, and the evolution of the main component xk is influenced by the control uk. So xk plus 1 is xk, yk, the observations, the control and the disturbance, where the distribution of this is given. So given the state xk, yk and uk, the distribution of wk is known. The evolution of other component yk will follow conditional distribution, and this will be unaffected by the control because it depends only on the state and not on the control. Okay, so it's so these are scenarios where some controls are dependent and sometimes not. So in this case, it might be intuitive to perceive yk as a disturbance. So here, if yk is observed by the controller prior to implementing uk, so if the control that I'm going to take, before that I do get a forecast, whereas wk takes effect post the application of uk. So there is a slight variation in yk, the way we see yk, the forecast, and the disturbance wk. So the forecast is something we observe. So that will be known, but then the wk that we will take is still a random variable. So there will be expectation with respect to w, and the controls that we will take, and then the disturbance will still be there, because wk might come from one of the distributions, but then it is a random variable. Okay, so a DP algorithm can be structured to operate primarily on controllable components of the state. Any influence from the uncontrollable component can be effectively averaged out. So let jk star xk yk represent optimal cost to go at stage k, and state xk yk is so this represents optimal cost to go for this cost. So this is the average average cost to go at xk. So it does depend on the forecast yk, and it also takes into account the uncontrollable component of yk, because we are averaging out over yk. So as with the parking example, a DP algorithm to compute jk xk will be given like this. So here from the outside we have the forecast, and we are taking average over the possible forecast, and then we have the cost inside, which is gk plus j hat, and we have the current state xk, observations yk, the control uk, and then we look for the cost at the k plus 1 onwards, and there is a expectation with respect to the disturbance w, and then overall we will minimize over the control uk. So this may look quite a lot, but this is the model that incorporates the disturbance w, and it incorporates the forecast y. So essentially overall what all this is saying is that things that are random, you just take, what you can do with random variables is only take average. So forecast in itself is what type of forecast will come itself is kind of a random thing, right? So there is an expectation with respect to yk, and there is an expectation with respect to wk. Okay, so with that forecast, what is the variations I will expect? So I want to go to play in a park, and then there is a forecast of rain which is 90%, and so on. But then what actually I will encounter will be wk. So there will be variations there. So this covers a good case where we can apply this. So we can derive this. I can like skip this derivation for the moment, and you may go over this a bit later. But what I want to do is that I want to go and derive the Tetris game, so that you get an idea of why we are doing all this forecast, disturbance, and how it's practical, right? So let us go into those things, and these derivations you can do it later. Okay, so one possibility that we have also seen before is assume that the forecast yk takes on values from 1 to m with the probability pi, then in that case our cost will be written like this. So basically this is expectation over yk, right? And now if we expand further on these, then we can write it here. So this will be our j star k. So there are different ways to kind of write the cost as well. So we can say that what is the, so if y k is can take one of these values I1 to m with probability pi, then for those forecast, the expected cost will be this, and then for jk star, if we expand it further, then this depends on the disturbance wk, right? And given that yk is I, so we can also do cost estimates in this way. So there you have a cost, the current cost, and then this is for k plus 1 onwards, and then overall with respect to the forecast, what is your expected cost estimate for those observations, and inside, obviously, as we did before, we take average over w. So so DP formulation for playing Tetris game. So let us see. So this is the Tetris game. We have seen this a couple of times now. So there are these blocks that comes down, and we are supposed to kind of so let us develop the good model for Tetris. So key points regarding modeling and optimal Tetris. So let us assume that this is finite horizon, but technically it's an infinite horizon. You can keep playing, although there is a from the Tetris app point of view, there are like certain number of levels where no one usually reaches that level, but people kind of keep breaking those levels. So, but as such, on paper, it could be seen as kind of infinite horizon, but for the sake of simplicity, let us say it is a finite horizon with long horizon. You see? So technically, when you play this game, it is like a finite horizon. It does terminate. You can't go beyond certain level because the speed increases the way the blocks fall.
But something unexpected is about to happen. He just became the first person ever to trigger a game crash, reaching the true kill screen, which is by far the biggest achievement in the 34-year-old history of the Pro Classic Tetris scene. So why is this such a big deal? And can a record like this ever be broken? To answer both those questions, we need to go back and start with the first unbeatable barrier in the game. In NES Tetris, released for the Nintendo Entertainment System in 1989, the goal is to assemble falling blocks to clear complete lines. For every 10 lines cleared, you move up a level and the speed gets a little bit faster. The fastest speed is reached at level 29, and at this point the pieces can no longer reliably get to the sides by holding down the side-to-side buttons. For decades, this was considered the end of the game, and level 29 got dubbed the kill screen because it always killed your run. Except it wasn't a kill screen in the traditional sense. In retro games, a kill screen normally refers to when it's impossible to get any further due to a glitch in the game's code. For example, in Pac-Man, the kill screen is reached at level 256, where a glitch garbles the entire right side of the screen and you aren't able to eat enough white dots to clear the level. NES Tetris doesn't actually have a glitch at level 29. The level is clearable if you can somehow figure out a way to move the pieces faster. And in 2011, Thor Ackerlund became the first person to reach level 30 on video by vibrating his fingers to mash the controller faster than the game's built-in speed, a technique known as hyper-tapping. And because level 29 is the maximum speed in the game, all the levels afterwards don't get any faster, so it was theoretically possible to go even higher. Thor's level world record would stand for 7 years, until a teenage hyper-tapping prodigy, Joseph Saley, broke it in 2018 by becoming the first player to reach level 31. Joseph's skill would allow him to win 2 Tetris World Championship titles in 2018 and 2019, and he slowly kept pushing the level world record upwards all the way to level 35, until an even faster hyper-tapper, Eric ICX, came along and became the first to reach levels 37 and 38. Now this was light years ahead of what anyone would have expected when the game first came out, but overall progress on the record was still slow because hyper-tapping only barely made level 29 speed possible. Deep runs into the 30s still required getting good luck with the pieces and near perfect placements with almost zero margin for error. In order to truly push things a lot further, some kind of breakthrough was needed. But then a new technique came along that would change everything. In 2020, a Tetris player named Cheese watched a video on various button mashing strategies and had the epiphany to combine a multi-finger technique by Hector Fly done on arcade cabinets and another technique that used a finger on the bottom of the controller to push it into another finger on the top. He called this new technique rolling, and it allowed him to easily reach button mashing speeds over twice as fast as the quickest hyper-tappers. He became the first player to ever reach level 40, and although a hyper-tapper named Alex Thatch would end up taking the record back, he would be the last tapper ever to do so. Over the next few months, there was a flurry of new records as most of the top players in the scene switched over to the new rolling technique, culminating in Eric ICX, now a roller, shattering the record in 2021 by making it all the way to level 95. With the fastest speed in the game now fully mastered, it seemed like the sky was the limit for how far players could go.
So, so what is state in Tetris? There is a board position. So we can use a binary vector that says which of the blocks are occupied and which are free. So that will be our the board position or the state. That is denoted by X. And then the shape of the currently falling block is denoted by Y. So according to our notation, Y is the observation that we will have. Okay, so this will be the shape. So what are the shapes we have? Like we have T block, we have S block, and O block and so on, right, in Tetris. So there are like 7 possibilities. The control U in Tetris will determine the horizontal position. So basically where you will put and the rotations applied to the falling block. So there exists an additional termination state which does not accrue any cost. If a state transitions to this terminal state, it will remain there without any change in the score. So obviously you don't keep increasing the score all the time. So a significant score boost. Yeah. So let us see. So let us see what is x, y, and u for Tetris. X is a vector of that will store whether these blocks are occupied or not. So x will be, you can think of this as a matrix, but then you can reorder this as a vector so that you have a long vector of 1, 0, 1, 0, and that indicates which of the blocks are filled or not. This is your x. Now y is the block that is falling. So this is our y, and u will be the control that that we will have to move these blocks horizontally or rotating these blocks. The shape y is generated based on some probability distribution py. So these shapes that we get, these come from some probability distribution, right? So what will be the next block? It follows certain probability distribution based on that. So it is not really round robin, so you cannot think that it goes in a cyclic way in some ordering. It is a random variable.
I wonder who designs the software that decides what Tetris piece to give you next. What was your random number generator? What did you use?
Well, I used the standard one. I had some problem with random generator because it starts always with the same number. So I need to put some kind of another randomness to start this random generator.
I have an interesting little story about that. Nintendo is going to master Game Boy Tetris. I got the version and I played it and I said, the pieces are not random. One of the pieces feels like it's coming up more than the others. So I got my QA people to count the pieces, and sure enough, one of them was, I don't know, 40% more than the others. And I told Nintendo, this is not acceptable. They sent their programmer to my office in Yokohama, and we worked together fixing the random number generator. Basically, we add 1 the first time, then we add 2, then we add 3, then we add 4, then 7, then we go back to add 1, 2, 3, 4. And so we spread that spike across all the pieces, and then it became random. Today, we basically created something called the bag system. And the way the bag system works is you take the 7 tetraminos, and you put them in a bag, shuffle, and then pay them out. Then you put them all back in the bag, and then you play them out again. So what that means is if the eyepiece comes out of the first bag and the last out of the second bag, it's 13 pieces later, you're guaranteed to get another eyepiece. And so that guarantee means you always know that at a certain point, the eyepiece is going to come out. Yeah, I kind of felt that the game lost something there, that fun part where everybody's watching you surviving at the top, and then the eyepiece comes out, and it's a big yeah. But if you already know that the eyepiece is going to come up, then it kind of takes away from that excitement, I guess.
It provides a little bit more of strategic kind of spirit to the game because you could build your profile in your mind before you actually do it. That's the strategy of the game.
I have an interesting little story about that. Checking into a hotel, and I have something to do with Tetris, and the guy goes, oh, why does it never give me the eyepiece when I need it? And I said, it's completely random. No, it's watching me the way I play, and it doesn't give it to you when I need it. I said, no, it's just random. No, I'm sure it's watching me. People attribute intelligence to randomness.
So that itself makes this problem interesting, that which block I will observe, I don't really know. So it will come via some probability distribution. The shape y is generated based on, let's say, some probability distribution py, and is independent of the control. Okay, so that is kind of independent of the control I take. I don't know what next will show up. Okay, so this makes it an uncontrollable state component. So for Tetris, the DP algorithm can be written like this. So this is an expectation over y, because y follows the probability distribution py. So we took an expectation over y, and then we have the cost inside, which is the cost. Now in this case could be the reward. This reward could be, let's say the block comes down and then you fill one row. So you put the block given the y, current y, and the actions that you took, the horizontal placement of the block or the rotation of the block, you did it in such a way that it fills one row, and hence you get a reward. So in this case, the reward will be, because usually we would like to kind of maximize the reward. So we can write it as max rather than the mean that we usually write for the cost. So in this case, G is like score. So the moment I complete 1, then the score will be very high. So this is what we want. And then for the future cost, k plus 1 onwards. So here G, X, Y, U represent the number of points scored equivalent to the rows removed, and F, X, Y, U determines the subsequent board positions, or if game ends, then it is equivalent to the terminal state. Okay, so we know how the game ends, because when one of the columns hits the top, then you can the game ends basically. The state represented by XY is represented by XY, and applied control is denoted by U. So you can think of state as this augmented one, where your current board position plus the Y that you see observe now, and that the information that you have is X and Y. That is your state, and based on that information you will take a control, which is U. So this is based on a finite horizon approach. We may also formulate an undiscounted infinite horizon problem involving a terminal state. So in this case, if we want to do it in an infinite horizon form, then we may. So what we recall is, from finite to infinite horizon, there is a finite horizon, there is jk, and when you go to infinite horizon, as if the cost is some j tilde, right? So we don't track the k in the infinite horizon, and that's where we get into this so-called Bellman equation, right? So everything seems the same, but we drop the k here. So j tilde is kind of like a some converged jk. So it's like some converged sequence, and then it gives me estimate of the terminal from any point until the end. So we can write this in the infinite horizon case as a form of a Bellman equation. So shape y is generated based on the probability distribution py. So basically overall this is expectation in y, and the value j tilde x provides an average score at position x. This is averaged over the values of uncontrollable block shapes y, and despite the simplification from omitting the uncontrollable part of the state, the quantity of x remains very vast. So we have seen this before, that the Tetris game, if we represent the state vectors as ones and zeros, then it can be very high. Depending on how many grid points are there, it will be 2 to the n, so which is the state space is very vast. So only suboptimal methods can address this problem. So in practice, when we solve a Tetris game, the state space is very big, and we are supposed to kind of even reduce this state space. So for the moment, we say that x and y is our current state, but then x is very big, and we need to kind of reduce this to some feasible state, which is much reduced. So if x lives in the dimension in the space, let's say 10 to the let's say 20, which is very big, but we want this x hat to depend on maybe 150, something like that, which is reasonable. So this is something we will see in future, how to do reduction in these big state space. So Tetris is seen as compelling and challenging stochastic problem for algorithm. It has many people have tried to provide various algorithms to solve. Initial papers were around 1986, and then Bertsikas 1996 again, and then later works were 2013 and 2015. And the consistent theme in these is approximation in the value space and various adaptations of the approximate policy iterations. And so this is approximation in the value space. Essentially also it's because the state dimension is very big, and the value space or the J depends on this X, which is very high dimensional. So you cannot really compute this for estimate this for all X. You need some neural network to do an approximation of the cost. Okay, so this is what it means by approximation in the value space. So that's pretty much like I won't go into so I won't go into the next thing. So I think we will stop here.